Select the major product of the following reaction. If we look at what we have, we are starting with a diene, and we are reacting this with HCl, hydrochloric acid. And so alkenes and hydrochloric acid, we know that these undergo electrophilic addition reactions. So we're going to be looking at an electrophilic addition. And the other hint we have is the temperature. And we see that we have negative 80 degrees Celsius. If you look at examples of these reactions in your book, you'll see two temperatures, the negative 80 degrees Celsius, and you'll see a temperature around 40 degrees Celsius, positive 40. And so this is the lower temperature that you will see, which means that we are looking for the kinetic product here. So the kinetic product is the product that forms the fastest. So if we are dealing with an electrophilic addition to a diene, our kinetic product is going to be the product of what we call 1,2 addition. So what that means in the case of HCl is it means the hydrogen adds on one carbon atom and the chlorine adds on the adjacent carbon atom. So if you're counting between those two additions, it would be 1, 2. So it will be the 1,2 addition product. And if it's going to be the one that forms the fastest, right, so the fastest, that means it's going to have to go through the lowest activation energy barrier, so the lowest possible EA, which means it's got to come from the most stable carbocation. So what we need to do is we need to look at our diene. We need to determine which one of those two alkenes gives us the most stable carbocation, and then we're going to do the 1,2 addition to that alkene. So let's take a look at the two alkenes that we have. All right, so our first option is we protonate this end alkene. So I'm going to draw the HCl. And I'm going to have my alkene do a nucleophilic attack on that hydrogen and break the bond between the hydrogen and the chlorine. These protonations of conjugated dienes will always give you the resonance stabilized carbocation. Do not even consider any carbocations that are not resonance stabilized. So we're definitely putting the hydrogen on the end and getting the secondary allylic carbocation. So here's the secondary allylic cation, and the resonance form of this we need to look at because the overall stability is kind of an average, a weighted average of the two resonance structures. So this is a tertiary allylic. This is looking pretty good. We could most likely stop here, but we should actually compare the second one just in case. So let's take a look at that. So here is our diene. Again, if I react this with HCl, I'm going to protonate here. And here's where you really want to watch what you draw. It's going to be really tempting to put the positive charge on that tertiary center. But if you put it here, that secondary allylic cation is more stable. So we're definitely going to put the charge here to have that resonance stabilization. So there is that secondary allylic cation. If we draw its resonance structure, because right now this looks the same stability as the one we just did, so we really need to look at this resonance form. And this arrow here tells us we're going to put the positive charge out on that primary center, which is not going to be as stable as the first carbocation that we saw. So that means that this is the carbocation we want to go through. If we added the hydrogen here, that's carbon number 1. That means putting the chlorine as a 1,2 addition would be on that second carbon. So we would therefore be forming this product. So there's the hydrogen added to the first carbon and the chlorine added to the adjacent carbon. And this was the most stable carbocation, so the one that would react the fastest. All right, and then considering our options, that is B.